Welcome. I will be starting shortly. Welcome to another episode of Microcontrollers with kingernorth. That's me. I'm your host, kingernorth, and this is episode 18, Trinket M0 with both CircuitPython and Arduino. So let's get started. Let's have a look at what we're using today. Alright, so here's what we're working with today. We have here an assortment of boards, and I'm going to explain what's going on here. On the breadboard here and here, those are the Trinket M0s, and one is connected and running CircuitPython right now, and the other one is connected and using Arduino. Both are actually active. They both have active programs in them, and we'll be going into that in a lot more detail. Up until now, we've been using this one here. This is the Uno, and there's Unos made by a number of manufacturers, but this is the standard type Uno, and this is the size of it. You can see it's actually quite large compared to the rest. It's an older technology. It was designed early on, and things were just a little bigger then. It used to actually have a big long chip along here on the original that was replaced with the small square one. But the whole thing is it had a fairly large footprint. Then in Arduino, when you wanted small, you went to this guy here in the middle. That is an ATTiny 85. That is an 8-pin dip chip. So it fits into a dip socket, so it looks a lot like the others. So just to show you there, let me bring that up. See if the camera will focus on that. That's just a little dip chip. That's just a little tiny chip. And let's see, it doesn't want to focus. Let's see if we can get it to focus. And I think that's it there. There it is. So there's the little chip. Little tiny chip like that. So there's that's an ATTiny 85. That has very, very limited memory in it. That's part of the problem with that particular. Let's get that camera back since I knocked it a little bit. Oh, I think I flipped it over too. There we go. Now we got it back in the right orientation. Okay, so we have that little ATTiny 85. And I can show that on the whiteboard there just to show you the size. It's a very, very small chip. The problem with these is you can't hook up the USB connection directly to that in order to program it. So what we have, and let me just move the Uno out of the way, because what I have here is a programmer board for doing an ATTiny. So what we do is, this is nothing more, and I'll show you. I'll take that off. That's an Uno underneath. That's an Uno that's been programmed to be a programmer. So what we do is we attach this other board to it, which I built up and wired up. And this holds the little ATTiny. So what you do with that, if you want to program with something that size, is you drop this little chip into here, in the top here. This is called a ZIF socket. Clamp it down. It's now in there. It's not going to fall out, and it's connected. And I can program it. And I hook up this with a USB cable. I take my program, I take my Arduino sketch, and I tell it to program through this to talk to that little chip. And then I have to remove it from here, put it onto a breadboard or something like that, hook it up, and test it. And if I don't like it, I have to unhook it, put it back in here, and reprogram it again. So it's very time consuming, but it makes a very, very small package. That's about as small as you're going to get in a chip that works with it, but it has very, very little memory in it. And you need a special, either you make one like this, or you can buy other ones that hold this chip and you can program it that way. So there are variations, but basically they're just the same thing in a different package. So you have to program it using another programming board. So that's what has to happen with that if you're using an ATTiny 85. And its counterpart is an ATTiny 84, which even though it has a smaller number, is actually a larger chip. It has more in and output pins, input and output pins on it. So that's one of the limitations. So we have the board the size of an Uno. We have this little ATTiny. Here, over here is our Circuit Playground Express M4. Or not Circuit Playground, pardon me. This is just a Feather M4 Express. So this is the Feather M4 chip that we've been using with CircuitPython. That's what I've been using for most of the weeks here. And I've been programming. And now we're going to switch to the little Trinket M0. We're going to go to a much smaller version of this chip. So let me move all the things that we don't need out of the way for now. And we're going to concentrate, and we're actually going to start with the Arduino board here. So I'm going to turn it this way. Let's see if I can get that in the center. And then I should be able to zoom in. And you can see it there. There's what it is there. There's the circuit we're building this morning on this. This is the actual board right here. This has got everything on it. And let me pull up the diagram here and I'll tell you what's on this board so we can get through it. Good morning, Walter. Welcome. So this little board here is actually quite powerful for what it is. And let's see, we don't want that one. We want to go over to here and I'm going to open it up there. So let me zoom in on that image because this is the board and this tells me all about all the connections on it. So I'm going to zoom in a little bit and you get it now, a pretty good view of that. So what we have here is this is the Trinket M0. So in the middle here, this is the processor chip. Instead of using the Atmel 328P that's on the standard Uno chip or using one of the other chips on here instead of an ATTiny, this Trinket was originally made with an ATTiny 85 on it, and they upgraded it to the SAMD21. This SAMD21 has a lot more power, and I'll go over that in a moment. But these are the connections. There's only a USB connector and 10 pins on this thing, so there's not a lot to connect to. That's what you give up with. That's what you give up for going to a very small format in size. So on here we have what they call VBus, which basically VBus is your USB. You have your V battery, which is the regulated power, it goes through a regulator. You have 3 volts down here, which is the regulated voltage on the board. You have a ground connection. So those are all your power things, and that leaves you with 6 pins left over. On those 6 pins, we have a reset button. So that takes up one of them. So you have a reset button physically here, but you can also have a reset connected remotely. And basically, it's just a push button going to ground. It takes care of the reset. Then we have 5 active pins that we can handle here. Now, these pins can do a number of things. So I'm going to take this image and I'm going to move it over a little bit because I want to show you these tags that are off on the right-hand side. These tags in purple are actually the Arduino addresses that we normally use, and we also mostly use those addresses within the CircuitPython as well. But basically what we have here is we have address 0, 1, 2. So this is pin 0, pin 1, pin 2. And over here we have pin 3, pin 4. So we have 5 I/O pins available to us. We also have pin LED 13. So if you're used to an Uno, one of the early sketches you usually do is you make this light blink. Well, they broke 13 out of here and put it down to a fixed LED. That's its resistor beside it. And the whole thing is that's all it does. It's only a light. It only has an output. It's pin 13. That's all it does. It just gives you a nice indicator light you can use. There are other features on this board. When you get into these here, if you notice beside these 3 pins, we also have green labels beside pins 0, 1, and 2. And they're actually pin A2, A0, and A1. They're not in the same order as the 0, 1, and 2. A0 has actually, when you follow through across here, has a digital to audio converter in it. So it actually does digital to audio conversion. So this is a true analog output if you want to connect a speaker to it. So this one has that capability. These other 2, A1 and A2, if you notice they have this symbol with the wave on them. These actually have pulse width modulation available to them. So they're actually analog, digital analog out. So we can actually drive a servo with them or send other parts of communication through that. Speaking of communication, you can also use A1 and A2 as SCL and SDA. If you remember from a while ago, and we've used it a few times now, we've used I2C communications. You can use those two pins to do IC squared communications. So this thing actually has the capability of talking to a display or other boards that use I2C. Quite a bit in it. Now let's move it over the other way and let's take a look at these other two pins. So these two pins with the purple letter numbers, they have they're pin 3 and pin 4. They're also analog 3 and analog 4. So again, these have analog capability to them. Something else I forgot to notice on the other side, but it is there. These two here, 3 and 4, can also be used as touch capacitive switches, which means you only have to bring a wire off them, and then you can actually use that as a switch without any other connection, a one-wire connection. So it has that capability to it. And again, they're pulse width modulation, so you can have digital analog out. You can also have analog in on any of these analogs that are here as well. Let's see here. Yeah, this center one here, the A0, which is the true digital. If you're not using it as a sound device, you can use it as a touch pin. So lots of choices on this thing. This thing actually has a fair bit of capability to it. Let's have a look at some of the features that are on this now. So I got to zoom this photo out so we can go to the next image. And it's right here. So what we have here is, they say here, this is right off of the Adafruit data sheets. So this says it's the same form factor and pinout as the classic Trinket. Remember I said the Trinket originally came out and it was designed with an AT85 on it. So if you had used a Trinket, written a program for AT85, the exact same connections can be made now with the Trinket M0. So there it is there. We took the ATTiny 85 and it was an 8-bit chip and turned it into a 32-bit M0 chip. Also what happened is it now has 256K kilobytes of flash as opposed to 8 kilobytes of flash that was on the ATTiny 85. So a huge improvement, 32, as they say, 32 times the amount of memory. Now we are dealing with 32-bit files, so they do take up more room than 8-bit files, but that's still a huge growth in available memory to you. Let's see, 32K of RAM on here. Well, it only had half a K of RAM before. So again, it's a much bigger increase in size of RAM to store files on and to do that kind of stuff with it. The speed of the processor, this is now a 48 megahertz 32-bit processor. The old ATTiny 85, basically it was an 8-bit it was an 8 megahertz processor on that. There was also a 1 megahertz version, but you could actually boot it up to 8 megahertz, which is what most people ran it at. This one has native USB support for all the OS, for every OS. So in other words, it can be used with Mac, PCs, on Windows, or on Linux. They all work. And it actually has all the standard connections for USB. The AT85, the ATTiny 85, like I showed you, we needed to hook it up to another programmer board because there was no USB on it. It can be programmed with Arduino or CircuitPython. We're going to do both today. So we're actually going to see how that works with both languages. It has a built-in green LED that just tells you that we have power on. We have a pin 13 LED, which is convenient for the red. It also has what they refer to as a DotStar. It's an RGB DotStar. This DotStar is very similar to a NeoPixel. It's a little bit different. A NeoPixel uses one line of communication with a power and a ground connection. A DotStar uses 2 connections for communications and power and ground. So it's a little bit different setup. And it's already built into the board, so it doesn't use up any of those I/O that are on the pins. And then it has 5 GPIO pins, which are available and not shared with the USB, so you can do whatever you want with them. So they're all available to you, and as we did, I talked about it, which ones were touch, the fact that you have a digital analog converter, and you also have pulse width modulation, so you have analog in and out and digital in and out on every pin. analog digital out was only on all but one pin because it has true analog out. So that's what's available to us there. And let's make the connection for the Arduino now. We'll start out with that drawing. So that's this one here. This is the drawing we're going to be doing today, and this is the board I'm going to be looking at when we program. And what I've done here is I've actually connected 4 LEDs externally to this item here. And what I've done is I've added just simple resistors. These are 220 ohm resistors with some 3mm lights. I've got one blinking as a warning light, and then I'm going to set up a red, yellow, and green as traffic lights. So I'm going to do both parts of that. I have that already running in there, but we're going to build it. And then we just have power and ground coming to the board. I brought power out, and we're not even using it, so it could have been left off. We do need the ground for the return for all the LEDs. Now the DotStar that's on here, I did give it a purpose. That's the DotStar. The DotStar is right there beside this is the processor chip in the big one in the middle. This little gray one beside it, that's the DotStar. So that light there, when we get this all hooked up, I'm going to have it mimic these lights up here. So it's going to mimic the red, the yellow, and the green. So if you mounted this remotely, you could look at the board and you'd know what color the traffic lights are. So it gives you that possibility to do that. So we got 4 resistors, all 220 ohm, a warning light, and 3 lights to represent a traffic light. And they're all going to run on here simultaneously. And we still have pin 4 available. There's no connection made on it, so I can actually hook something else up to it too. So we have a lot of flexibility with this thing. So let's go ahead and turn that off. And let's have a look at what we're going to do with the program today to make this work. So as we can see here right now, just to show you the final product that it's running, we have a warning light back here, okay, towards the back, and it's just blinking at a regular rate. In here, I actually have it, and even though it looks washed out on the screen, that is a red LED currently. And that is actually the green LED that's on now, so that would be the green LED that's lit. And then after a few seconds, it goes to yellow, and then it goes back to red. So it's just cycling through the traffic light signal. And of course, you could add 3 more, and then you could have a traffic lights for the opposite direction. If you were modeling this on a train layout, you might only see the one direction lights. They could be there. You could have a warning light set up somewhere else, and you could have something else going at the same time off of this. So you actually have a reasonable amount of flexibility just on this one little board itself. Gives you lots of choices. Surprisingly, lots of choices. So now let us look at the main program over here. So I have my empty Arduino sketch set up here. And what I'm going to do with it is I'm going to go in here and I'm going to do file save as, because we always have to tell it where we're going to create the program. So let's do save as. And on here, I'm not going to put it in my Arduino window. I'm going to go ahead and, where's my documents drive? There it is, documents. We'll go down to our show folder. Yes, episode 18, we're already down to that. So we're going to go into here, and you can see I have a bunch of stuff in here, and let's give this a name. And this is going to be Arduino Lights. So there it is there, and we're just going to hit save. So now it's called Arduino Lights up here in the corner. So let's throw in a comment at the top. This is just Arduino Lights by kingernorth. And this is to test the features of a Trinket M0. Okay, so that's our start. That's what we're going to do. And one of our next things we always add in here is we're going to include any helper files. All right, we don't have any to start with, so we're going to actually get around that. We're not going to worry about that. We are going to have to do a couple of things here. We're going to have to define some pins. So let's create all our pins and variables. So create all pins Got to get little fingers for today. Pins and variables. So that's what we're going to start with. So what we're going to do is we're going to put in a few things here. Now we can define them or we can do them as integers. Sometimes if we define them and it's a very small number, it'll actually use less memory. So because memory is limited in Arduino, and it's actually not going to be bad on this board, I'm going to go ahead and I'm going to use the word define. I could just as easily put in integers. So I'm going to say define, and I'm going to call this one my, what is this one going to be? This is going to be my warning light. So this is going to be a warning light, and this is the warning light pin. And I'm going to set that to pin 3. Okay, and then I'm going to add the next define. So I'm going to create another tag here, and this one's going to be the red pin. And this is going to be on pin 2. I'm going to have to add my other part of my traffic lights too as well. So define, and I'm going to create a yellow pin on pin 1. And I'm going to come down here and I'm going to define my last LED, which is my green pin, and that's going to be on pin 0. So that's where they're all going to be in there. So those are in good shape. So those are all the pins that we need to do. So we're going to move on now to the setup. So let me just move down here to the setup portion. We're going to highlight this, and we're going to set the pin modes. So we're going to do that. And we're going to start out here with pin mode like we normally do. And I hope looks like my audio should be fine. I'm not dropping any frames. Whatever we had happen those couple of weeks in a row there doesn't seem to be happening now. So I'm happy with that. Pin mode. We're going to start with the warning light pin, and we're going to set that as an output. So that's an output, and of course, because we're not using define, we have to actually put the semicolon at the end of the line. This is Arduino. So now let's go over here, and I'm just going to highlight this. So I'm going to copy. I'm going to move down a line, and I'm going to go paste, 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 since I have 4 pins to do. My next pin was the red pin. Then I had the yellow pin, and then I had the green pin. So there we are. We have 4 output devices, so we're all set there. So we're in good shape. So what we've done so far is we've included no helper files. We've defined our 4 pins that we're going to have our LEDs connected to. We have actually created the 4 LED objects by creating them as outputs. So they're ready to go. We've set those pin modes, so we know how we're going to use them now. And we're going to move on into the main program. So one of the things here is I want to do with the with this is I'm going to have to go in here and I'm just going to get rid of this line completely, because we don't know what the comments are going to be because we have to put them in. So actually just let me do that, and we're ready to add comments once we figure out what we're doing here. So when we're doing this, one of the first things we want to do is we want to probably read in some time, because we're going to make this warning light flash on a regular basis. Thanks, Walter, for confirming that the audio is good today. And so let's get back to this warning light. So the one thing we're going to do is we're going to use the internal clock in the chip. And it's accurate to a fairly good degree. So we're just going to create a counter, basically, is what it is, for current time. So let's create a variable called current time. And we're going to make that equal to, and the way we read the internal clock is we use mils as a function. And what that does is it reads us in the milliseconds that are happening inside on the clock. So it gives us this nice long number, and it just keeps adding to it. So it works out really, really well, but it's in mils. So we can deal with it that way, which is really kind of nice. And we're actually going to take that clock, and we're going to have to add some variables up here when we get to it. So let me just go through and do a couple of things that we need to do. So the next thing we're going to do is we're going to create the warning light system here. So we're going to put in a comment, and this will be the warning light. So that's what's all going to go in here. And in order to do that, what we need to do, we want to give it a bit of a strobe effect. We want to have an on and off cycle, but we don't want it on and off for too long. So what we're going to do is we're actually going to do an if statement in here. We're going to create an if because this way the loop continues. Because don't forget, we're going to do a second function by getting the traffic light working. If we're doing that, we're going to need timers. So we're going to create ourselves a timer here. So we're just going to say if current time is greater than, and in this case it's going to be warning light on goal. So this is when we want the light to turn on, we want this time to be greater than the current time. So we're going to go ahead and we're going to throw that in, and then we're going to do something based on that. If this is achieved, if current time is greater than the goal time, what we want to do is we want to turn the red light on. So we're going to turn that light on. So we're just going to go in here and do a digital write. And we're going to write to pin W light. And this is going to be the W light pin, and we're going to set it to high. High is effectively going to turn it on. So that's what that's going to do. And then what I want to do is I'm actually only just going to use a delay that's really, really short. So we're talking like 20 milliseconds. So I don't mind delaying this within the program. And then what I'm going to do is I'm going to go and do a digital write. And I'm also going to make this on W light pin. And this time, instead of making it high, I'm going to turn it off, and I'm going to turn it off for a period of time. Now, I have to do something about setting this amount of time. Well, I don't want to use another delay because I want it to be about 1 second before it comes on again. But I don't want to pause the whole thing for 1 second because then my traffic light can't work. The traffic light's going to keep waiting all the time. So what we do is we cheat with it, and we do a little bit of math here in our program. And what we're going to do here is we're going to take this goal time that we had up here, the W light on goal, and we're going to make that equal to current time, whatever time this whole process started, and we're going to add, let's get a space in there, we're going to add 1,000 to it. So we're going to add 1 second. Actually, yeah, 1,000 is lots of time. So we're going to add 1 second to it. So what happens here is this becomes a 1 second delay from the time it started, and then it's going to come back, it's going to turn on for 20 milliseconds, and it's going to be off for 980 milliseconds of that 1 second cycle. So that's what we want to do here, and that's what we're getting with that little blinking light. If this is all correct at this point, well, the one thing I haven't done, I didn't create these variables yet. So I need to create those up in the top here. So we better create some of those. So what I'm going to do is here, I'm just going to add in here, because this is my pins and variables. So in here, I'm going to do an unsigned long is what we use for time. That's the data type that it likes for it. So we've got to create one for current time. We need to know that. So that's our current time. We also need one for the goal time that we're doing. So we got the unsigned long, and this is going to be the W light on goal. And to start it, we can use it and just set it to 0. We're actually going to give it a value. I don't care what the other one is because it's going to set right at the beginning of the loop. But this one here, we're going to actually set the time. So we're going to say set it to 0. So the very first time through this loop, it's going to turn it on and turn it off and then keep looping around. And it's just going to keep doing this until we tell it not to. So let me validate this sketch to make sure it's working, or at least that it thinks it's coded properly. So we're compiling right now. It says compiling. The first time through takes a little bit as it's trying to figure it out. And I should have set the board type to it when you start. You should do that because I'm not using my Uno, which is the normal default. We'll see if that makes a difference here in a moment. Like I said, it does take a while to compile the first time, but it did it, and it says it's done compiling. So now let's go up here. And because I was playing with this the other day, I do have the Adafruit Trinket M0. Now, you have to go into your boards manager and you have to add it. But once you do, I have access to all of these different Adafruit boards. And there's and way off on the right-hand side that you can't see is a Trinket M0, but it says it right here in the first part. It's set up here as Arduino. So that's what it's doing. We don't want it as a tiny USB because it's actually something else it can do. Debug is turned off. We don't want to turn that on. Only turn that on if for special features, and that's an advanced feature. We can see here that the Trinket is recognized on COM27, so it's on COM27, and everything seems to be fine here. So I'm going to go ahead and upload that, and we should see these lights here, these traffic lights turn off. One may stay on if it was on previously, so we're going to find out. So it's compiling the address right now. And once it compiles again, then it should upload. There it is, it's uploading. And it was much quicker this time for compiling. All my lights are out on the board right now. And there we have. We have a blinking light. So we have a warning light going. About once a second it comes on, and it comes on for a whole 20 milliseconds. So there we go. We have our warning light, and that's the only thing that's running on here. And if you notice that this is a kind of a bright purple, it's actually more of a, I guess, a mauve color. That just tells you that it's okay, the DotStar. It's something that that's programmed into it, but we're going to see how to change that shortly. So that's what happens there. So now what I'm going to do is I'm going to go ahead and I'm going to cheat a little bit by adding in my traffic light for you. So I'm going to add in my first part of my traffic light. And the first part of the traffic light is the red light. So I'm going to copy some code because we're not going to have time to do everything and get to the CircuitPython. So I'm just going to come down here. I'm going to paste that code in. And when I do, it says here, turn on red traffic light. So now again, what I do is I look at that current time. Is it greater than the goal time? And is red the next light to come on? So there's actually two conditions that are required in this if statement. First of all, did the current time go past the red goal time? And if it did, and red is the next light to come on, then go ahead and do this. And what it does, it says, hey, set the red pin high, set the yellow pin low, set the green pin to low, so only the red light will be on. Then it says green goal, because when we look at a traffic light, if it's red, the next light we expect to see as a driver would be the green light. So we actually have to set the green goal. The green goal would be set to current time plus 10,000, so it's going to wait 10 seconds. Then it's going to say green next is going to be true, and red next, which was true to get into here, is now going to be set to false. Now I also have some other things in here, and I'm just going to comment this out for a moment so it doesn't affect it. And that's for the pixel. That's for the DotStar. So we're going to get back to that. So right now, that's what that does. So that's going to turn on the red light. So now let's see what it needs to do to turn on our green light. So if we come down here, we'll paste into here. Here's the green light. So green would be next. So green says if current time is greater than green goal, which we set when we were in the red cycle, and green is next, then it's going to say, hey, make the red pin low, make the yellow pin low, set the green pin to high. So it turns on the green light. Then it sets current time plus 8.5 seconds. It's going to set yellow next, and it's also going to set green next to false. And again, I'm going to highlight these out because we're going to do that as a separate step so we don't do too much at once. And let's get the yellow traffic light, because without it, we're not going to have a completed cycle, because it's going to cycle to yellow before it goes back to red. So let's do that. So we come down here. And we have our yellow traffic light. It has the exact same pattern. It's just our current time is greater than our yellow goal, which was set in the green cycle. It's going to say, and yellow is next. It's going to say, set the red pin to low, set the yellow pin to high, set the green pin to low. It's going to add 1.5 seconds. So that's how long the amber is going to stay on, or the yellow light. It's going to set next goal true for red. It's going to set yellow next as false. And again, let's turn off the DotStar function, just so we don't get any errors with that because I haven't set it up. And what are we missing in this program? There's one thing. Okay, I'm only going to give you a moment to think about it because we have to come back up here and we have to add all those new variables we just added for all the different colors. So let's get ready for that, and I'm going to go find them in my other program. And they are way up here. And I'm going to come into here and I'm going to paste them in, and let's see what we added. We added, again, these are timing functions, red goal, yellow goal, and green goal. And they're all set to 0 by default, so they're all set as unsigned long. Same as the current time and the warning light goal time. So anything to do with the timer, internal timer, we want to set it to unsigned long. Next, we want Boolean values for next, red next, yellow next, and green next, just that they're true or false. And by default, I set red to true, so it has a place to start when we load up the program. And the other two are set to false. So the first thing it's going to do when it gets down to here is it's going to say current time is greater than red goal. Red goal was 0, so it's going to say yes. And is red next? Yes, it is. So then it will go ahead and do this, and that'll start our traffic light. If this is all good, let me do a validate. This will tell me if I missed doing anything, because I haven't added in all the DotStar features yet, because we have to set that up. And it compiled. So you know what? We're going to go ahead and upload it, and we're going to see the traffic light work and the warning light work now. So currently we're compiling. So down here in the corner of the screen, there it is. It's going with the green bar down here. Now it's uploading it, and we will see this board update here shortly. And there it goes. We have a red traffic light. We can wait the few seconds because it was a 10-second cycle. Then it'll go to green, which is the one furthest on the right. There it is. It's going to be 8.5 seconds there. Then from there, it's going to move into the yellow. It's only going to stay there for 1.5 seconds, and then it's going to move back to red. And in the meantime, our warning light continues to do its flashing, independent from the traffic light. So this is how we get the two of them combined here. Now, the last thing I want to add, just to make this program really nice, and this is just a big cleanup, is we're going to add the DotStar. So let's go ahead and start adding the DotStar, and I'll bring you through that. Step by step is what we have to do in the program. So for this, we are going to need a helper file. We need to include the helper file for the DotStar. So we'll put that in there. And this is include Adafruit DotStar.h. So this is a library that we have to save. Now you can go to your libraries. You can look up Adafruit DotStar and just add it to your list. And it'll be available in your library from there on. So that's what you want to do with that. So that's the library. The next thing we have to do is the big part. And what we have to do is we have to create the DotStar object. So now that we've used the library, let's create the DotStar itself. So I'm going to come into here, go down a couple lines, and I'll paste this in here. And let me move to the beginning of this line here. And it says create the DotStar object. First of all, we have to define how many pixels. They still refer to them as pixels, even though they're not neopixels. They're DotStar pixels. So how many pixels are there? So the number of pixels is 1. There's only 1 built onto the board. Okay, and it's that one that's in mauve right now shining on the screen. The connection pins, and this is going back to that drawing that we had earlier. So if I go back to here, and I back up a couple of images and enlarge, I'm going to go to here, and it gives me information about the DotStar up here. So the DotStar in purple uses pin 7 and pin 8. Pin 7 is the D pin, and so we have two. We have a data pin and we have a clock pin. So that's the data pin is pin 7, and pin 8 is the clock pin. So we actually have those labeled here. That's labeled as D1 for data input, or DI for data input, and CL, even though they look the same on the second part, that is actually for clock. So it's pins 7 and 8 that we use on here. So they are labeled already in our program as digital pin 7 and clock pin 8. And then what we do is recreate the actual object, which is the Adafruit DotStar number of pixels, we put in the data pin, we put in the clock pin, and then we set the color for it. And the color for this particular one happens to be DotStar, and it's blue, red, green. Instead of RGB, it's actually BRG for this version. Some DotStars are RGB. This one happens to be a BRG version. And you can play with that pretty quick and you'll learn which one it is without much trouble. But this was all obtained from a helper file on the Adafruit website where it talks about this example, and I brought in an example into Arduino and played around with it and got it working. So that's how we get the DotStar running. And what we need for that is we don't need any pins defined because everything is done up in this where we're creating the object. So there's nothing further to create there. What we do need to do is we need to start it up in the setup. So just like if we were to use the print screen and all that stuff, we put that in here. We have to go into here now, and we have to go into the void setup, and we're going to have to turn on all this stuff for the DotStar. So let's do that. So basically, the first part's really simple, is we have a DotStar begin. It looks just like it does when we use serial begin. We have a DotStar begin, and that initializes it and sets it according to those pins that we used when we created the object. The next thing we do is I set the brightness. This brightness is actually adjustable. You see I have it at 10. That's extremely low, but it'll be plenty bright for the camera. It actually sets from 0 to 255. So we're going to be on the really low level. By default, it comes up very bright. I'm not sure what the setting is by default on the board, but it's bright. Then what I'm going to do is I'm going to clear all the information that's in the data line, and then I'm going to show it, which is going to turn off everything. So that mauve light that you see there on the screen, oh, I guess you can't see it on the screen. Better turn that off. That'll probably work better. Okay, let's go back over this again. Aha. Include a helper file. I did that. And create the object pins. I did that. I showed you how I got 7 and 8 in the picture. The next thing I went down here, let me explain this part again because I think I had it covered up. We want to set up we want to turn it on. So this was star.begin to initialize the pins. We set the brightness to 10, which was what I was just talking about. It's adjustable from 0 to 255. Star clear tells it to remove all the data from the data line. And star show tells it pump out the new data, which since I cleared it, there is none. It'll tell them all to turn off. So even though there's only one, it'll tell that one to turn off. Okay, so that's what happened there. Didn't get too far in before I realized I was missing it, so that's good. So when I do this, instead of that mauve light being on over here on the board, when I turn it on, it'll actually turn off right now. But I want to take it one step further. So in my program here, I actually have it for setting the pixel color. And the way this works is I'm using star.setPixel. So let me just get rid of the comments in front of it. And I've got star.setPixelColor, and it's going to set pixel at the first number in here. There's 4 numbers. The first number is which pixel am I setting? And since I only have one, it is pixel 0. So it is going to be pixel 0, set it to, and it's BRG. B is 0, R is at 255, G is at 0. So that'll give me a red light. I go down to the next one. This is my green. Now, I just said it was BRG. For some reason, it likes GRB when you enter them. This is trial and error sometimes. So I actually have that set to 255, which will give me the green. And in the last one here, I have these values in here. I played around until I got a yellow I was kind of happy with. NeoPixel seemed to set a little better for colors than DotStars, but they both work. And this one here, you have to set some green, some red, and you get a yellow out of it. Don't use the blue. So that's everything there. So it should be okay. I'm going to say, let's validate before I try sending it, uploading it. We're going to see what happens here. Hopefully it works fine, and it says it's compiling right now, so it'll only take a moment. It's done compiling. So let's go ahead and do this now, and let's upload that. Now we're going to see things change over here. So right now it's doing its compile again before it does its upload. It should be just about finished. There goes the green bar. It's now uploading it. You see the light change to green, then it goes to mauve, and then it actually shut off and went to red, and it went much, much dimmer. And that red is matching the traffic light. So when the traffic light goes to green, this dot star goes to green. Then when this goes to yellow, it'll go to yellow. The dot star will go to yellow, and then it'll go to red. And we'll see that. There's yellow, and there's red. So there we have it. We actually have a program working. So we've created an Arduino program here on a unit. Now, one thing you can actually see, and it's hard to see down here, I'm going to go over here and I'm going to move the screen up. There's lots of stuff that happens in the background here in the board that you don't normally see. And this is going through and doing all of it. This is the important line up here in white in the whole bit. Sketch uses 16,504 bytes. Okay? Remember, we only had a limited amount of flash when we were doing this as an ATTiny 85. But because this chip has so much more flash memory in it, what's happened is we're only using 6% of the program storage space to run this. So if you can imagine, we wrote 70, 80, 88 lines of code, and we only used up 6%. You could write an awful lot more code and a lot more features into this before you'd run out of space. So we're only using 6% of the programming space on that chip. We can use a lot more if we want. So this little chip, I'm only just scratching the surface of what it's capable of doing. And that's the idea between this version of a Trinket with the M0 chip as opposed to the original ATTiny 85. This thing has way more memory and much more capability to it. So I could hook up a ton more things to this, or have it do a lot more with the pins that I have exacted. I could actually be surprisingly a lot with this particular setup. So that is how it works with Arduino. Now I'm trying to get myself some decent time here. I want to go through the CircuitPython version of this. So let me swap out boards here. Let me move that one out, and I'm going to move this one in. And this one here is a circuit we've done before. So first of all, let's go look at that circuit. So I'm going to come up here, and I'm going to have to zoom back out, and I'm going to have to get over to my circuit that I want. This is the circuit on the Circuit Playground version. So this is the one with CircuitPython on it. So this one here is connected up. The first thing we have is an infrared emitter and a detector. So what I'm doing is I'm just hooking this up to power, and this is sending out a signal across here in infrared. The detector receives it and sends that back to pin 3. Pin 1 and 2 are actually connected to my crossbucks. So this is a grade crossing flasher, is what this is. This is representing my grade crossing lights. So this is just 2 LEDs. You could have 2 more LEDs for the opposite direction or on the other side of the crossing, and for the roadway, to protect the roadway. And we have 2 LEDs here, and they're just connected again. These 2 LEDs are connected with 220 ohm resistors. The emitter has a 220 ohm resistor on it. The detector is done a little different, where it's actually got a 10,000 ohm resistor on it connected to ground to give me a ground on the input lead when I'm blocked. So if I'm blocking here, because I actually have power going to this detector, if this is blocked because of the condition that it is either seeing light or not seeing light, it will see a ground on the input. When this turns on like a switch, it will allow current to flow, it'll allow voltage to flow, and what happens is here we will see a voltage on this, a high input on here, and we can read that as a high input. So that's what we do to it. I also have 2 empty pins here. Now, I am using light 13, like an LED on D13. I'm using that to tell me when it's not blocked. So if I see a signal across here, based on that signal, so if these two are aligned, in other words, this is emitting and this is detecting, then it will turn on the LED. If it gets blocked, this LED will turn off. When it turns off, these flashers start flashing, because that tells me a train is blocking the detector. So it's telling me to start the flashing lights. So that's what's happening there. Then when you unblock it, you'll see the red LED will come back on, but these lights will continue to flash for a few seconds afterwards, because what happens in here with this detector, you might see the gap between the cars as the train cars are passing by the detector. So because of that, it may not be a steady input coming in. We need to allow for those pulses. So until I see it gone for 3 seconds, I'm going to keep the flashers going on the grade crossing. And I've actually got I've used the DotStar in here. I've actually got it set to go blue while these are flashing. So while these are in the flashing mode, this will stay blue. So I've got a bunch of different things that are happening here. So this is just giving you an idea of what's going on. All right, so let's turn that circuit off, and let's turn that off, and let's turn on mu, and let's have a look at what's inside this program. So I'm going to go through this program, and you're going to see we're going to get to the items pretty quick in here. So at the very top, this is my Trinket test by me, kingernorth, using CircuitPython 5.3.1. This is the current stable version of CircuitPython out there. Helper files, as in always with CircuitPython, a lot of the stuff is not preloaded into it. You have to tell it to load up. So again, we're going to do that. We're going to import the board. We're going to import digital I/O, or from digital I/O, we're going to import digital input and output and direction. We're going to import Adafruit DotStar as DotStar, so we're going to bring that in, and we're going to import time. First thing we do is we create that object, just like we did when we were doing it in Arduino. We're going to create the DotStar object in here. So I'm going to do that. So star, I called it, just like I did in the other one, I called it star, is equal to DotStar, DotStar board, and then these are actually the communication ports. If we went back to that drawing, we can actually look that stuff up, and it's inside the written instructions for the helper files. And then I'm going to have the number of pixels is set to 1, and the brightness is now set to 0.2, which is 0. It goes from 0 to 1. So the minimum is 0, the maximum is 1, not 255. And then I use my star.show, just like I did in Arduino, to turn it off, basically, because there's no data in it yet. So I'm doing that to turn the DotStar off. Next thing I'm doing is I'm setting up my pinouts, just like I did on, I set up my pins, and then I created the objects for the pins in the setup file. I do that all the same time here in CircuitPython. So this is very simple. I have an LED. So what it's doing is that's the built-on board LED is on D13, and I've set the direction as an output. I've created an object for red 1 and red 2, which are the two crossing grade lights, and basically they're set up on inputs D1 and D2, and they're outputs, I should say, and they're actually set as outputs. And the last one is my infrared in. That's the yellow wire that was on my drawing, and that is set up to pin 3, and that is set up as an input. And I'm just reading a discrete input from that infrared. I'm either reading that it's around 3 volts or around 0 volts. So I'm just reading it high or low. I've created some variables in here, not as many as I did on the other one, but I have some variables. And I created LED flash is equal to false. Added time is equal to 3, in other words 3 seconds, because it's 3.0. Extended time is equal to 0. Cycle 1 flash is false. Cycle half time is a half a second, so that'll be the flip-flop time. It'll be half a second on, half a second off for each of the red lights. So I could change that in here and change the rate of flash. And it's going to say how much time has passed, and it's 0. So here I go here with the main program. We're already into the main program. There's not as much setup really in the beginning with CircuitPython. But I do want to show you how fast you could change things. So we're actually going to do this at some point. In here, I'm going to, again, just like I did in Arduino, I have to grab the current time from the internal clock. So this time it's called current time is equal to time monotonic. Monotonic is what reads in the millisecond time. And it brings it in a decimal fashion too. It actually puts the decimal in it so that when I add numbers to it, I add them just like I would as if I'm using a regular timer. Everything's in time base of 1 second. Whereas in Arduino, we use milliseconds. This uses full seconds, but the milliseconds are being read in the background. Now what we're going to do is we're going to set a couple of conditions for this input. And it says if infrared in value, so if I can see it, it's not blocked. So right now, if I turn on the serial monitor, it tells me it's not blocked. It tells me that at the bottom of the screen in the REPL. If I put my finger between it and block it, it changes to the word blocked. So it does that here. So here's where my print statements is, and I'm getting a real-time feedback saying whether it's blocked or not. And I can change that just by moving my finger in between and away from the emitter and detector. So I can see that. The other things that I'm doing here is I'm saying, is the LED value, I'm going to set it, if it is blocked, set LED value to true. If it's not blocked, set it to true. If it is blocked, set it to false. And then what I'm looking for is LED flash. If it's blocked, I want to set that to true. I want to start those lights flashing. This LED is the D13. That's the little LED in the corner. So as I move it in and out, you can see that little LED way up here is reacting to me blocking or not blocking the signal. So it works really well. And then if I do block it, I take my extended time equals current time plus added time, which is the 3-second delay that I want to keep the flashers flashing. And then what I do is I create a slight delay in here because this thing is so fast and it's talking to the serial port here. It's using the USB as a serial port to talk back to me because I say print LED flash, which is the false or true. And I have to put in a very slight time sleep. So I put in 100 milliseconds. I can actually make it a little quicker. But basically what that does for me is make sure that I don't lock up this program. Because if I get rid of all my print statements, I can actually get rid of that timer and it'll work just fine. But I actually need it for the serial connection because it's not as fast as the chip is. Remember, this chip is much, much faster than the original. This is running at 48 megahertz as opposed to the original 8 megahertz that we had on an Arduino. Then what we do here is we say if it's set to LED flash, then it says make the LED flash on and off. And basically during cycle 1, we say that red 1 is on and red 2 is off. Otherwise, if it's not cycle 1, then red 1 is off and cycle 2 is on. And it says here, if current time is greater than cycle half time, cycle 1 equals not cycle 1. So basically that flip-flops it every half a second, and here's where it adds the half a second to it. And then we have down here is turn on DotStar. So what I do is, if this is actively timing and going through and running, I set my DotStar 0, because it's the first DotStar in the bunch, and I set it to a value. And again, even though it's a BRG reading, it actually comes in as actually it's a BRG DotStar, but it reads as GRB in the data input. So we actually set B to 255, which is blue. And then we tell it to update that. If this LED flash is false, what I do is I come down here and I set the flash rates to false and turn off the DotStar. But flash is going to stay on for an extra amount of time. And this is where I have that extra time set. So if the current time is greater than the extended time, LED flash is false. So what happens here right now, we can see here that I'm not blocked. I'm set to false. My flash is set to false. When I block it, it says blocked and my flash changed to true. Now very quickly, if I do this, you've got 3 seconds to see it, but if I move my finger away from there, it will say unblocked, but it will remain to say true for flashing. And then after 3 seconds, it'll go to false. And there it goes to false. Also, when I block this, I am flashing my blue dot star in the middle of my board is on. When I remove my finger, it remains active until it says to stop flashing. So I'm actually able to utilize the features that are on the board to do this. Now I talked about how fast we can make changes. You saw how long it took to upload the file in Arduino. I just want to show you how long it takes to change something and upload it here in CircuitPython. The easiest thing for me to change right now is the flash rate. So you can see how fast the lights are flashing when I've got it blocked. Okay, so let's go into the program. My half cycle time is there. Let's make my half cycle time, we'll go to an extreme. We'll make it 1.0. So I doubled the amount of time. And all I'm going to do is hit save. And there it is, it's done. It's already updated. Look how much slower those lights are. The update was so fast, by the time you looked at the program, it was already running on the board. It's very, very fast. So any changes are very quick. Well, you know what? Let's make this ridiculously fast. So I'm going to go to 0.2. I'm going to watch the board, because what's going to happen here is I'm going to save that. It's saved. Now if I do that, look how fast those flash rates are. That might be okay if it's a police car and you have a red and a blue light up there, but it's not so good for a grade crossing. Maybe a little too fast. Maybe you find 0.4 works better to your style. I can change it again, and I can do that. So you just have to decide what works for you. And if you really want to fine tune this, I can say 4.425. Let me save that. And there it is there at just over 0.4 of a second. 425 milliseconds for each half. So very quickly I can go in and edit this file. I can make a lot of changes to it very quick. I can look at it through my REPL, which is the serial port. And it's a short program. So it's 77 lines of code. The other one was 83. Basically it's similar in size. They're not a huge amount of difference in size. CircuitPython is definitely faster to edit. It just takes a little different setup to get used to. But this board, the same board, can be programmed, as you just saw, they're identical boards. One was programmed with Arduino. The other was programmed with CircuitPython. And both work very well. So there we are, we're blocked. We got the lights flashing, and that'll just keep working. Nice simple circuits. This is something we can do in our time. I'm hoping that this is an advantage, is helpful to you. One of the things I plan on doing with this is I plan on getting more of these, because there's a lot of times when I don't need to use a full-size board like the Uno or the M4, and these are obviously cheap. These are relatively cheap boards. I think they come in around the $8-9 US mark, which may seem not real cheap, but they are compared to the regular price of boards. The only place you're going to beat anything cheaper is if you buy the Uno board from China, but to buy an actual Uno board is about $20 US. To buy the equivalent board in that M4, I think, is around $19. It could be 21 or 22. There's an M0 version as well. So they're similar in price, the CircuitPython and the Arduino boards, of similar design. In fact, actually, even Adafruit makes an Uno board which is cheaper than the Arduino board, but it works just the same way. But this is still cheaper than either one of those. Like I say, this is around an $8-9 US mark. I think what I'll do is when I need to fill orders up, when I'm putting in my orders to the US, I like to order a given quantity. Just makes my shipping and everything cheaper because it is coming international. And I'll be filling my orders with one or two of these boards when I can, just to get them in stock, and so I can use them for little projects and dedicate them out to little quick projects on the layout. I think they're great. They're versatile, simple to program in either language, so it's whatever you're more comfortable with. And the whole idea is to have fun. So here we are. We used the Trinket M0. We created a grade crossing circuit today. We also created a traffic light and a warning light, and we did it all with simple programming. So I hope you've enjoyed. If you're familiar with this, oh, why did it go back to that picture? There we go. That should work better now. So we have Twitter is at kingernorth. That's my Twitter handle. You can get notifications there. You can also go to YouTube, and of course, this is the YouTube channel here, kingernorth. Make sure you give me a thumbs up for the video if you enjoyed it. That would be great. While you're at it, make sure you subscribe. Let your friends know about it. Other people in the hobbies, or whether it be electronics or in model railroading. Let them know about this. They can get some ideas maybe themselves. And on Twitter, please subscribe. And that would be it. So thank you very much. Have yourself a great weekend. For those living in the same area where I am, basically enjoy your long weekend. This is a holiday weekend. Have fun. And we'll talk to you again next time. Thanks very much.